Okay, guys, in this video, we're going to talk about current and resistance and basically try to introduce a few key concepts for circuits. Now, this video is basically going to focus on resistors. It's going to establish kind of the core concept of resistors for us. So, on the agenda is to talk about current just a little bit and circuits. I'm relying a little bit on y'all to remember some of your middle school stuff here, so if there's knowledge gaps there, we can talk about it during the debrief, but I think y'all should remember most of that. We're also going to talk about resistivity, the resistance formula, and then we'll talk about ohmic versus non-ohmic behaviors for resistors. The video goals here are first to introduce circuits and current. And again, you guys should understand circuits a little bit from middle school, but we'll briefly reintroduce a couple things. And then we're going to define resistivity, differentiate ohmic and non-ohmic resistors. That's a really big one for AP. They really want you guys to understand the difference between what it means for something to, for a resistor to exhibit ohmic behavior versus exhibit non-ohmic behavior. And the last thing we're going to do is calculate resistance of a resistor from its physical attributes. Oh, and I didn't put this on the goals in here, but we do also want to introduce Ohm's law, but that kind of goes hand in hand with the ohmic and non-ohmic stuff. So first up for resistors, or for circuits. So you should be familiar with the idea of a circuit, something that looks, kind of like this. You'll have something like a battery, and then maybe you have something hooked up to the circuit, and you've got a current flowing through that circuit like that, right? Now, what the battery does is it supplies a potential difference, and we've unpacked that term enough that hopefully you're comfortable with that, but basically what that means is it's supplying a potential energy. That potential energy is basically going to help charges to flow in a certain direction, and in fact, it establishes an electric field in the wires that causes those electrons to move, and they're basically moving from a region of high energy to a region of low energy, as everything else typically does. There's lots of analogies that people use of waterfalls, where the water flows from a high point to a low point, and you can think of it the same way, where charges are going to flow from high energy to low energy. So you could see that one of these terminals has a higher potential energy than the other, and so they naturally will flow to the lower potential energy unless they're inhibited in some way. Now, really important here is we should touch on what's actually happening in the circuit is that electrons are flowing. So you can see the little electrons flowing through the circuit like this, right? Now, that's what actually happens, and we know that because protons can't move. But electrons can. However, we didn't actually know that for a long time, and we had kind of figured out a whole bunch of stuff with circuits before then, and we'd already kind of created this convention of thinking about positive charges flowing. And rather than correcting everything, we just kind of said, well, let's just pretend like positive charges are flowing. And so there's an important distinction you have to understand between actual electron flow and what we call conventional current. And so basically from this point forward, we'll always talk about things in terms of conventional current. And so that's going to be basically assuming that charges flow from a positive potential to a negative potential. So we've seen this pop up before, right? With all of our other stuff, we kind of assume positive charges. Same thing here. So from this point forward, I'm going to switch from electron flow to showing conventional current. I want you to see, I'm going to switch back and forth a couple times. We're just showing that the flow is reversed, because it's kind of at some point splitting hairs to say that negative charges are flowing clockwise versus positive charges flowing counterclockwise. It's kind of just an accounting trick to go back and forth between the two. So from now on, we'll communicate in terms of conventional current, talking just about charges flowing in kind of the positive loop, from the positive terminal of the battery to the negative terminal. Now, I think it's worth mentioning here very briefly a little note about how we draw batteries. So you see this battery here in the more electron scheme. I'm going to turn off the current flow for a moment. What I want you to see is that one side of this is longer than the other, and it's going to be really important moving forward to understand that when you look at circuit diagrams, that the long end is the positive end. Okay, just as a little note. And we'll talk more about circuit diagrams as we go, but the long end is the positive end. Okay, so let's talk about current. So current is the rate of charge flow. So charge is flowing around that circuit, and we want to know basically how quickly the charge is moving. Now that's not in terms of velocity, it's just how quickly the charge is moving. We could talk about the velocity of charges, but that's this thing called drift velocity, which AP does not get into so far as I can tell, so we're not going to worry about that. Now, if it's the rate of charge flow, we basically imagine a cross-sectional area and how quickly charges are passing through that hoop, and that means it's going to have units of coulombs per second. Now, a coulomb per second is a mouthful, and so instead what we call it is the ampere. And the ampere is also a bit of a mouthful, and so we kind of shorten it to amp. So anytime you've heard amps, the amp is referring to 1 coulomb per second. And so over here, if I take an ammeter here, which is something that measures current, and I put it over a location, you can see the current flowing through there. This one's supplying 1 amp of current. In other words, 1 coulomb per second. Now, resistivity is a really important concept, and it's basically the concept that different materials are going to resist current flow differently. They all do a little bit. We will tend to idealize wires to say that wires have no resistance, but in general, everything is going to resist current just a little bit, and how much they resist that really depends on the construction of the material. And it depends on the structure internally of the material in particular. So we should know that electrons flow because they've got a loosely bound structure, and different types of materials are going to be bound tighter or looser than other materials. And so it then stands to reason that it's going to be easier to get the electrons to move in some materials than others. And that quality of how hard or easy it is to pass a current through something, we call that resistivity. And in our equations, we use the variable rho for it. Also important to note here that temperature can play a really big role in the resistivity of an object. So resistivity tends to change with temperature change. And in fact, we may talk at the end of the year for just kind of some fun topics about like semiconductors and superconductors that may conduct differently at different temperatures. Now, resistance is different from resistivity. So resistivity is the basically how a material behaves. Resistance is how a particular object behaves. So it's the resistance of a particular resistor. And so that's going to depend on, first and foremost, the resistivity of the material, right? How easily electrons move is going to be really important. But it's also going to depend on the other physical characteristics of just like the dimensions of the object. So it's going to depend on the length of the object. It's going to depend also on the cross-sectional area of the object. And so we have a formula you can use here. The resistance is equal to rho L over A, where L is the length of the resistor and A is the cross-sectional area of the resistor. Now, resistors can be classified in two ways. They can be classified as ohmic resistors, or they could be classified as non-ohmic resistors. And what it means to be ohmic is for there to be a linear relationship between voltage and current, which basically means that as I increase the voltage across a resistor, I'm going to see the current increase the same amount. And so let's go back over to this circuit constructor and I'll show you what this looks like. So here you can see that right now this battery is putting out 10 volts. And at 10 volts, I get 1 amp of current. So if this light bulb behaves in an ohmic way, then for every 10 volts I increase the potential, what I should see is that the current goes up another 1 amp. So let's look at that here. If I go up to 20 volts, hold on, let's get on there. There we go. Yeah, I've got 2 amps. If I go up to 30 volts, I'd expect 3 amps, and I do. If I go up to 40 volts, I would expect 4 amps. And so we can see that this light bulb here is behaving as an ohmic resistor. It is going to have a linear relationship. And I've got a little graph of what that looks like here. So you can see the green dots here represent an ohmic behavior. So you can see that at 10 volts, I had a current of 1 amp. At 22 amps, 33 amps. And you can see it's a very nice linear behavior. That's considered ohmic. Now, another thing we need to know about, though, is non-ohmic resistors. And those are ones that the resistance will actually vary with the voltage. And typically what we see here is that the resistance varies a lot at the lower voltages, but then when you get to higher voltages, it tends to kind of level off and reach kind of an upper bound. And so I'll show you what that looks like here. So if we come over here, I'm going to remove, let me actually reset my battery first. We'll say put it back at 10 volts. Oh god, that's too much clicking. Okay. And I'm just going to cut this guy off and not do you. By the way, you should notice, and this is review from middle school, that if the circuit is broken, then no current flows, just as a reminder. But let's go down here, and that was an idealized light bulb. I actually have a real light bulb here. And what we'll see is that real light bulbs do not behave in an ohmic fashion. So here I've got 10 volts and 0.54 amps. Now what I would expect is that if it behaved in an ohmic fashion, when I increased the voltage to 20 volts, I would expect that to double. Double the voltage should mean double the current. So that would mean it should be at 1.08 amps. Let's see what we get when I put it up to 20. Uh-oh, it only went to 0.85 amps. So that doesn't seem linear, but maybe it's just linear in a different way. I don't know. Let's see what happens when I go to 30. Okay, it actually went down even less than it did the first time. And then up to 40, it went up less than the first time once again. And so I've made a graph of this behavior as well, so you could see that. So if I go over to this tab here, this purple represents that non-ohmic light bulb. And you can see that the graph clearly is not linear. It levels off after a time, and it doesn't increase as rapidly. So that would be a resistor that's considered non-ohmic. And the truth of the matter is that most resistors kind of have a range of voltages for which they behave ohmic, and a range of voltages for which they do not behave ohmic. But for this course, we basically just lump them into two categories. We can say a resistor is ohmic, or we can say a resistor is non-ohmic, and it really depends on that relationship. If I get a nice linear relationship between voltage and current, that is ohmic. If I get something that curves like this, we would say it's non-ohmic. Another way to put that would be to say that ohmic is governed by Ohm's law, which is this equation right here, V equals IR. Now I want you to notice that this is not exactly the graph that I put before, because my graph was basically current as a function of voltage, because that's the way that I collected the data. But I could easily reverse it. So let's go look at that graph reversed real quick. So if I come back over here, you can see I've got voltage and current here. Well, this other graph, I'm going to turn off the green one. The blue graph is voltage as a function of current. I'm not going to change my labels. You just have to ignore those. And so if I resize here, you can see that it's still linear. And actually, the slope of this line then would be the resistance of the resistor. It would be the resistance of the resistor. And so I could kind of check that here and do a little, Y1 is proportional to, let's say, R for resistance X1. And let's see, hold on, that was maybe not the best choice. Let's go M. There we go. So here you can see that I've put this this equation here. Oh, and that's my first graph. That's why it's looking funky. Let's try 2. There we go. And now you can see the slope of this line is 10. If I go back over to my little simulation here, I'll show you. I just got to get rid of this guy. I go all the way back up. I'll show you that the light bulb actually does have a resistance of 10 ohms. So if I turn on the values, you can see its resistance is 10 ohms. Which also, a bit of an oversight. It bears noting back on kind of the resistance slide that the unit for resistance is ohms, OHMS, and we use omega as the unit for that. Okay, so there you could see Ohm's law carried out. V equals IR, where the slope, the relationship between current and voltage then, is R. This Ohm's law is a hugely, hugely, hugely important law that we use a ton in this course. So you're going to see it a lot. But it bears remembering that not every resistor actually behaves in an ohmic fashion, and so it may be worth questioning whether something does or does not as we're kind of tinkering a bit. Now, let's go back to our video goals here and make sure we've touched on these. So we introduced circuits and current. We talked a little bit about what current is. It's measured in amps or amperes, which is a coulomb per second. We define resistivity, resistivity being the actual resistance of a material to current flow. We differentiated ohmic and non-ohmic resistors. So the difference is that ohmic resistors are going to have a linear relationship between voltage and current. Non-ohmic resistors do not have a linear relationship. They tend to change as the voltage increases or decreases. And then last, we should be able to use that equation, the R equals rho L over A. We should be able to use that equation to calculate the resistance of a resistor based off of its physical attributes. So that's gonna end it for today's video. Hopefully some of that made sense. In class, we'll start by looking at tinkering with some resistors a little closer.